Welcome to our first learning workshop of the semester. It's significant figures. And significant figures is one of the more difficult topics um, that come across in introductory chemistry and even in general chemistry. And one of the reasons that this is because most professors are kind of in a rush and they don't necessarily have time to go into why we use significant figures or what they even are. Just kind of tell you, okay, how do you find the number of significant figures and here's how you calculate with them. But we're going to go look at this a little bit deeper because if you understand why, then you'll understand how to use them and why using them is important. And I think it'll make it a lot easier to use them. So the short answer to the why is why significant figures? Why do we use them? They are a solution to the problem of measurement. And so let's talk about what that means. So measurement is artificial. It's an artificial way to, and when I say artificial, I don't mean that in a bad sense, but measurement is something that human beings have been doing for a very long time. It is our way of trying to quantify something that cannot easily be quantified. So we come up with some sort of standard and we quantify it. Think of like the IQ test for measuring intelligence. It's in a way it's almost arrogant in the way that we try to quantify something like intelligence. But there are other things that's more natural to quantify and we can do so more consistently. So from earliest history, mankind has begun trying to quantify things, particularly things that would be useful to communicate between people. Like, so in ancient times and biblical times, you'll see like in the Bible, the unit of a cubit is used. And cubit, what is a cubit? Well, a cubit was the length between your elbow and the tips of your fingers, and that was the best they had. Because they got to figure out something that everybody can use, that anybody can easily access, and we can relate. It's like, well, I want some rope. Well, how many? I want 20 cubits of rope, or I need to build a house. Okay, I want the house to be 10 cubits long and 15 cubits wide. You know, um, so these cubits, the problem with them is that depending upon if you were tall or short, if you were a child or an adult, your cubit was very significantly different. So as time went on, our standards have become better. Eventually we went to a foot, and the foot was really, the standard was the king's foot, okay? So since there was only one king, everybody used the measurement of the king's foot, and therefore there is a consistent standard throughout the kingdom. And of course, that kind of became codified later on in the English measurement system. The foot was just set to be a certain length, and we just kind of went by that. Um, Now, our current standard of a meter was originally just a platinum iridium bar that they held in a museum in Paris, and all meters were measured based on that standard. All meter sticks were compared to that standard. But consistent standards are important because we need to be able to have a standard that is somewhat universal so that if I measure something, that it actually makes sense to you. Like if I say, I need 16 L flops of water, you'd be like, what on earth? But if I say I need 16 liters of water, you'd be like, oh, I know what a liter is. Yeah, you have an idea of how much I'm talking about. So as science of measurement has evolved, standards have become much more consistent. But no matter how good a measurement gets, it can never be perfect. So when we have a measuring instrument, we try to measure how long something is. We can never measure it perfectly down to the exact, atom or micrometer, like a picometer or something like that. There's a certain point beyond which you just can't estimate perfectly, or you can't measure perfectly how long something is, or how much volume there is, or how bright it is. Um, so how well we can measure is based upon the accuracy of, or rather the precision of the measuring instrument. So before we get into measuring, we want to talk about different kinds of numbers. There are two different kinds of numbers that we deal with in chemistry. There are exact numbers and there are measured numbers. Now, exact numbers are usually pretty easy to tell because they are numbers that can be counted, um, or they are numbers that are definitions. Okay, so exact numbers, because they're exact numbers, they have no uncertainty. They are perfectly precise. They have unlimited precision, absolutely certain. So, like for example, the number of people in this review session is an exact number. You can't have like 3.5 people or 5.5 people or 5.2 people. It's going to be a whole number of people, a counting number, an exact number. So as a result, um, anything that's counted is going to be an exact number, including like the number of atoms in a particular molecule of water. There's 2 hydrogen atoms and 1 oxygen atom. Okay, well then the other type of exact number is definition. So, um, or the other type of number is measured numbers. So measured numbers are used with a measuring device, and therefore they have uncertainty. It's limited by the accuracy of the instrument itself. So as I mentioned already, exact numbers are counting numbers, but they can also be definitions. So definitions like 1 foot equals 12 inches, even though we use a foot to measure and inches to measure, even though we use meters and centimeters to measure, the relationship between centimeters and meters is based upon a definition. A centi means literally 1/100. So a centimeter is 1/100th of a meter. Therefore, there are 100 centimeters in 1 meter by definition. So those would be exact numbers. And you'll actually see those in conversion factors because you're going to be, have you done anything with converting yet? Have you done any conversion or dimensional analysis yet?
No.
Okay. You'll be doing it very soon. And when you do, um, we'll keep in mind that exact numbers are not going to change your significant figures of your answer. Okay.
Okay.
So, oh yeah, go ahead. What were you going to say?
No, I said okay.
Okay. So let's take a look at these as some examples. So, in 1 yard equals 3 feet, is that an exact or is that a measured number?
I think
I
that's
think
a
it,
measured number.
actually those are exact numbers. 1 yard equals
Oh,
3 feet is a definition, and so since it's a definition, it would be an exact number. But I definitely understand why you would make that mistake. What about the diameter of a red blood cell? Does the diameter of a red blood cell 6 times 10 to the negative 4 centimeters? Is that exact or measured?
I
What do you,
believe should be measured.
measured? Absolutely. That is a measured number. What about there are 6 hats on a shelf?
Exact.
That's exact. Very good. And what about gold melts at 1064 degrees Celsius? Exact or measured?
Ex exact.
Almost everyone says exact the first time around, but that is actually a measured number. Temperatures
Okay.
have to be measured because the truth is, um, uh, even though it's kind of a definition in the sense that gold does melt at a specific temperature, but the problem is the measurement of that temperature is not precise. It depends upon a thermometer, and the thermometer has fluctuations, which is why it's actually really interesting. If you go into different um, standards, go into different books, different textbooks, you'll actually see different values for some of these things, like the amount of heat released or the melting point of a particular substance. Like some textbooks might say the gold melts at 1062.5, others will say it melts at 1064.2 or something like that. So there's definite fluctuations, and it just depends about the circumstances under which the temperature is measured. Okay, cool. So what are significant figures then? Now that we've dealt with that, as I've written here, in simplest terms, significant figures are the numbers that reflect the degree of certainty to which a value is measured. In other words, they reflect the precision. Significant figures are a measure of precision. And why do I say precision as opposed to accuracy? It's because the precision tells you to what degree of repeatability can you make a measurement. If you have a particular measurement with a particular measuring instrument, that measuring instrument should allow you to measure the same way every time within the within a certain degree of error based on that measuring instrument. So all the measurements should be relatively close to one another if done with the same measuring instrument. However, that measuring instrument could be wrong, it could be off, it could be badly made, and therefore the numbers would not be accurate. But significant figures indicate the precision of a measurement. So to measure, when we're actually measuring items, measuring volume, measuring length, the number of significant figures can be determined by measuring all digits that are known with certainty, plus one estimated digit. So you need to go one digit beyond the smallest markings. So if you have a digital instrument, it'll automatically do the measuring for you with appropriate significant figures, like a digital scale. But for non-digital thermometers, meter sticks, graduated cylinders, anything like that, for those things, you're going to have to actually measure between the smallest markings, estimate between the smallest markings. That's estimating one digit. So let's take a look at what that means. So here's an example of a graduated cylinder here, and this part is blown up. As you can see, it's blown up, zoomed in, and when we're measuring with graduated cylinder, you'll notice that there's oftentimes this little dip. In the graduated cylinder, if you have liquid in it, the liquid kind of dips down a little bit. Okay, you can actually kind of see it here. Okay, I'll go ahead and draw that line over. It kind of dips down a little bit. It's not super big here, but it is a little bit. You can tell the dip. Well, whenever you're measuring a graduated cylinder, whenever you're measuring the volume, you always measure from the center of the cylinder, and usually that means measuring from the bottom of the dip. Okay, so measuring from the bottom of the dip, if we're looking at this, we can see clearly that the tens place is known with certainty. So, in other words, we know that this volume is between 10 and 20. It's between 10 milliliters and 20 milliliters. That's easy to see, right?
Yes.
But the next one, the ones digit, is also certain, because we can see 16, 17. I have a 4-year-old and a 7-year-old. I know exactly how you.
Yes. I'm a 4-year-old. I'm a 4-year.
And that is totally fine. If they come in and say hi, I don't mind.
Okay.
But you can see clearly with these markings, I've labeled them. They're not labeled, but it's 15 and 20. I've labeled them 16, 17, 18, and 19, and then there's 20. Okay, so there's 5 intervals, and I've labeled these markings. I can see clearly that the volume here is in between 17 and 18, right? It's in between 17 and 18, so I know that this is 17 point something. The ones digit is certain. Okay, so what I need to do to measure this volume to the appropriate number of significant figures is to estimate between the smallest markings. If I imagine 10 equal markings between 17 and 18, What would I say this is? 17 point what?
0.5.
17.5. That's a really good estimate. That's about what it is. One could make the case, you could try to say, well, I think it's maybe just a little bit higher. Maybe it's 17.6. Or somebody might say, oh, it's actually a little bit lower, maybe 17.4. But 17.5 is probably the best estimate, although those others would be acceptable too. Note
Okay.
that it's not going to be perfect, and you will get a range of answers depending upon who's measuring, but they should be close. So I'd say 17.5 or 17.6 would both be good answers here,
Mm-hmm.
and that's how you measure with the appropriate number of significant figures. Estimate between the smallest margins.
Okay.
So another thing, and this is more important when we actually get back into the lab, um, if you do any sort of lab work, whether it's in the context of a medical lab or whether it's in the context of a chemical company, whenever you're reading these graduated cylinders or this glassware, you always want to make sure that you're reading at eye level. So
Mm-hmm.
if you are too high, the what's known as a parallax error will occur, and it'll make it look like it's down here. Will get which gives you a low reading. You'll think that the volume is actually lower than it actually is. Likewise, if you
Okay.
look at too low, it'll look like it's higher than it actually is. And so you
Mm-hmm.
always want to read from eye level. And I already kind of mentioned this a little bit, but you always read from the center of the tube. For water, it usually means the bottom of the meniscus. But
Mm-hmm.
for mercury, like in mercury thermometers, we always we still look at the center, only this time it's going to be the top of the meniscus rather than the bottom.
Okay.
Cool. So let's take a look. Let's practice with these, okay? These are a couple of
Okay.
examples. Go ahead and measure what you believe the volume is in these two images, A and B. Measure the volume and just write your answer in the chat. Well, what's your question?
Yes, I think B, I got 7.5,
Okay. And what?
and A, I got 53.1.
Okay. Well, let's take a look at those and let's see how we did. So, going back to the PowerPoint, um, if we're looking at this, I'm actually going to go ahead and mark this up just a little bit. So, you got 51. This is 51, 52, and this third line here is 53. Now, we're measuring from the bottom of the meniscus, from the center of the tube. So that means we're going to measure right about here. Okay? So that means the volume is in between what
Okay.
two numbers? The volume is in between what two numbers?
51 and 53.
Well, it's between 51 and 53, but furthermore, it's between 52 and 53, right? It's between this line here and
Yes.
this line here. So it's between 52 and 53. So it's 52 point something. And um,
Mm.
and our other student, I think, actually got it just about right, 52.8. Now, one could make the case that that is perhaps not quite high enough to be 52.8, maybe 52.7, but 52.8 is a pretty darn good estimate. So great job on that. Um, if you said 52.7, that would also be fine. You could even probably get away with 52.6. I think it's a little too low to be 52.9. But yeah, it's going to be around 52.7, 52.8. That's probably your best measurement of that. That's a little tricky, I know. That's a little tricky. Now let's take a look at the next one. The next one is the uh, one, and this one is really tricky because it actually there's two numbers in between the between the big marking here is 8 and the big marking down here is 6. There's two numbers between, so 7 is the halfway point. 7's the halfway point. And because there's 5 markings, there's 5 spaces. 1, 2, 3, 4, 5. Uh, that means that each one of these is actually 0.2 instead of 0.1. So this is 6.2, and this is 6.4. Okay, and almost nobody, in
Okay.
fact, I can't remember if I've ever had a student to actually get this one right on the first try. I think I have maybe, but almost nobody gets this right on the first try because it is hard. It is really tricky because of that extra fact you're going by 0.2s here. So that bottom of the meniscus is right about there. And if that's 6 point, well, it's clearly between 6.6 and 6.8, right? Here's your 6.8 and 6.6. So the bottom of the meniscus is between 6.6 and 6.8. Now it's a lot closer to 6.6, and there's a lot of flexibility here. One could say that this was, 6.62. One could say that 6.6. You could make a case for 6.64, although I think that's a little bit high, 6.63. But there's going to be a little bit more uncertainty here because you're going by 0.2s instead of 0.1s. So really anything between 6.1 or 6.61 and 6.65 is probably reasonable for this particular measurement. Does that make sense?
Yes.
Mm-hmm. So a good job, both of you. I mean, it, it's not easy tackling these right off, and honestly, y'all were quite a bit closer than I usually have. So that's good. That's good. We'll get some more practice in. You're gonna be champions at this before we're done. All right. Now, what about the length? So here's how we do length. This is actually a little bit easier to see. We don't have to worry about this meniscus stuff. Um, this is actually in centimeters, even though I know these are really big centimeters. It's really blown up. But if I was measuring the length of this line, I can see, here's a halfway point. Here's a halfway point. That's about 1.5. That means that this line, if I'm measuring it, is in between 1.6 and 1.7, right? Now, there are no smaller markings between 1.6 and 1.7. What do you think? Is it closer to 1.7 or is it closer to 1.6?
Well, closer to 1.7 for me.
It is a little closer to 1.7. I would agree with that. So if you were going to estimate, what would you say this is? 1.6 what?
1.6, 1.65.
Okay, but you said it was closer to 1.7. 1.65 is exactly in the middle.
Oh yes. Well, yeah, 1.75.
Well, if you 1.75 is going to be right here, right? 1.75 is going to be right there. It's between 1.6 and 1.7. You could say this is 1.6, probably about 1.67. You could say 1.66. 1.66 would not be
Oh yeah,
bad
it's
either.
closer to 7.
Hmm.
Hmm.
But yeah, so you're estimating this number. It's closer to 1.7, so this should be a little higher than 1.65, but it's definitely less than 1.7. So 1.67, 1.66, that's probably about the best estimate here. And because that last digit's uncertain, we can't estimate anymore. Because if I write 1.67, it could be 1.66, right? It could be a little bit less, couldn't
Yes.
it? Yeah. It's hard to tell.
Yes.
Let's go ahead and measure this one. And when you have a good measurement, go ahead and punch it into the calculator, or not calculator. Punch it into the chat. Let me know what you have.
Which one we're doing?
Uh, the one that I'm showing right now, the measuring the length of the wood, the wooden stick.
Where you have the red marks?
Uh, well, let's see. What's showing up here? Yeah. Oh no, here we go. Yeah, the wooden stick. So there's a wooden stick. There's a
Okay.
yeah, the 5 centimeters. Measure the length of that wooden stick. What would you say that is?
4.5 and a half.
Yeah, 4.5 and a half, which means basically 4.55, right? So that's
Yes.
absolutely that's excellent. That's excellent. 4.55 it is. You could one might say it's a little bit past, could say 4.56, but you wouldn't want to say 4.5 because here's the deal. If I say here's what you have to understand. If I say 4.5, what I mean is that this is plus or minus 0.1. In other words, it could be that zero point 0.5 is estimated. It could be 4.4, it could be 4.6. But the thing is, 4.4 is right here, right? And 4.6 is right here. I'm not uncertain about it being between 4.4 and 4.6, right? Like that's not estimate. Like if somebody said 4.4, that's totally wrong, right? This is this is clearly not 4.4. So I can't use this. This is not accurate. It's not that doesn't indicate the level of precision that I have with this instrument. However, if I say 4.56, that means it's plus or minus uh, 0.01, which means this could be as little as 4.54 or as much as, or little as 4.55 rather, or as much as 4.57. And if I'm looking at this, if I'm looking at where this ends here, could that be 4.55? Seeing how this is 4.5, could this be 4.55 centimeters long? The end of the stick? What do you think? It could, couldn't it?
Yeah, it could.
Hmm? It could be 4.57. Maybe it's the edge of
Yes.
it extends a little bit further than I see. Yeah, it could be 4.57. So there is some uncertainty there. So this number much better reflects the uncertainty of the measurement. This number is the much more, this is a correct number to use to express the appropriate number of significant figures. And so that's what significant figures tell us. They tell us the degree of precision of a measurement.
Okay.
So I used to have measuring stations when I did this in person, and I'd have people go around the room and just measure with the different instruments. Unfortunately, we can't do that with the at the moment since campus is being closed. However,
Yeah.
we can go forward and learn how to calculate and identify significant figures here. So um, as I mentioned before, the last digit, when you see a number, when you're given a measurement like this, the last digit is the uncertain digit. So a number like this means that means the mass is somewhere in between 54.06 and 54.08. In other words, it's plus or minus 0.01 grams. However, if I get a number like this, the uncertain digit is this one, and therefore the significant it's plus or minus 0.00001 grams, or 1/100,000th of a gram. This is a much more precise measurement with a much more precise measuring instrument. So when we're given numbers, measured numbers that have already been made for us, we need to be able to identify how many significant figures there are for the purpose of keeping track of the uncertainty. And one of the ways that we do this is the rules of zero. Now, it's always obvious if they're significant figures if they're non-zeros, but if they're zeros, it's not as obvious. Um, Therefore, we have these three rules of zero, and they are leading zeros are never significant. Now, leading zeros are all zeros before the first non-zero number. So none of these are significant. Even though there's a decimal here, none of these numbers, none of these zeros are significant. The only significant figures are the 2, the 5, and the 9. Now, that doesn't
I
mean
can't
that,
see what you're doing right now.
oh, you can't. Uh,
Mm-mm.
let me take a look at
Okay,
it.
now this is out.
Oh, that's so weird.
Okay, now it's good.
Okay, let me try that again. Can you see it now? Can you see what I'm doing?
Yes.
Okay, so yeah, so those leading zeros are never significant, but uh, any non-zero number that's reported with the measurement, like a 1, 2, 3, 4, 5, 6, 7, 8, 9, any non-zero number is automatically going to be significant, but the zeros are sometimes not significant. So leading zeros are place value holders. They're important, they are necessary, but they're not significant figures. We're not going to call them significant figures because they don't indicate the level of precision of the measurement. Likewise, sandwich zeros, zeros in between non-zero numbers, these are always significant. So they always count as significant figures. So in this case, this number would have 5 significant figures. And then the last rule of zero is, and this is the trickiest one, trailing zeros, zeros after, specifically after the last non-zero number. So zeros after the last non-zero number are only significant if there's a decimal point, okay? Which means in this case, these zeros are not significant. They're after the last non-zero number is this 5 here, okay? And these zeros are after the last non-zero number, but there's no decimal point. So they're not significant. This number only has 3 significant figures. However, the 12.500, these zeros are significant because there is a decimal point. So this number actually has a total of 5 significant figures. Now there is a reason for this. The truth is, there would be no point in having these zeros here. There'd be no point in having them there if they weren't telling the degree of precision of the number. And the reason is because without those zeros, it's still 12.5. So those zeros are there to tell me that this measurement is accurate to the nearest 0.001, to the nearest 1,000th. Okay. However, with no decimal point, then I can assume that those zeros at the end, with no decimal point, these zeros at the end, I can assume they're just place value holders. They're just telling me, they're just keeping, if I remove those, 12,500 becomes 125. Well, you can't have 12,500 become 125. So these zeros are just there to hold the place value. But the actual uncertainty in this measurement, according to this, is plus or minus 100, because the last significant figure is that 5, which is in the hundreds place. Does that make sense?
Yes.
Any questions on any of this so far?
No. Good.
Okay, cool. Let's do some practice. So how many significant figures are in this first number here? Significant figures are also sometimes called significant digits.
6, right?
You got it. 6 significant digits, 6 significant figures. So how many in the next one? How many significant figures are in the next one?
3.
3. Good, because leading zeros are never significant. These are leading zeros. Don't count. Now we still need them. They're still important. They hold face value, but they're not significant. So 3 sig fig. How many significant figures in this next one?
Oh, that one's a little short. Is it 8?
Not quite. So remember, these are still leading zeros, right?
Oh, they are? Okay.
Yeah, because there's zeros before the first non-zero number. The first non-zero number is
Mm,
this 2. However, you
okay.
also have these trailing zeros, and these trailing zeros are significant because of the decimal point. So that makes this a total of,
Oh, 5?
yeah, 5. 5 significant figures. Now, how many significant figures are in the 4800?
2?
Actually, because there's a decimal here, which means
Oh,
that these trailing zeros here are going to be significant. The trailing zeros don't have to be after a decimal. They're just
mm,
zeros at the end of a number, zeros to the right of the last non-zero number. Because of that decimal, all these zeros are significant, so that makes this 5. What about the next one, the 4800 here? How many significant figures is that?
is it 5?
No, this one is only going to be 2. See, there's no decimal
Oh, no,
here.
okay.
Yeah, there's no decimal here. So because of that,
Oh,
these
yeah, I was
significant.
looking at the one with the decimal. That's why I said
Oh, yeah,
5.
yeah. Yeah,
But,
no, that one, yeah, you're right. That one had 5. But this one only has 2 because trailing zeros don't count without a decimal.
yeah.
All right. Now, with scientific notation, let's see if you got this. How many significant figures are in this value? This one right here.
Is it 3?
Actually, it's 4. And the reason is this. This part here, the times 10 to the 6,
Mm-hmm.
actually does not affect the number of significant figures at all. What that 10 to the 6 does is it tells you place value, tells you how where each of these other numbers should be in reference to um, the ones place, tens place, hundreds place, etc. So this times 10 to the 6 just tells you place value. So there's no significant figures in that part. However, each of the rest of these is a significant figure. So this would be 4.
Okay.
Does that make sense?
Yes.
All right, how many significant figures in this last number?
Is it 6?
It is 6. Very good. Yep, you got your sandwich zeros, so they're always significant, and a trailing zero with a decimal, that's also significant. Very good, very good. Excellent. All right, so when we're actually doing calculations with significant figures, we end up with a situation where we're always having to round them. We round the significant figures because the number that comes out of our calculator is not necessarily going to have the number of significant figures that we need. So let's say we do a calculation and the answer is supposed to have 4 significant figures. But this is what we got out of our calculator. So what you do in that case is you count left to right the first 4 digits, the first 4 significant figures. So 1, 2, 3, 4. The last significant figure is that 5. Okay? You
Mm-hmm.
round that up or down based on the number that comes after it. So here is the number that comes after it is this 0.
0.
Now because of that, is the 4965 going to round up or is it going to stay the same?
They're the same.
It's going to stay the same. So this is going to round down. It's going to be 4965. So with the next one, once again, I count my significant figures left to right until I get to 4. 1, 2, 3, and 4. then what's the number after the last significant figure in this case is 8. So is that going to round it up or down?
Up.
It's going to round it up. So that 5 is going to become what?
6.
A 6. Now here's the thing. I can't lose track of my place value. The place value must remain the same. In other words, this 5 here is in the hundreds place. So when I write out my answer, I can't simply put 7806. Because if I do, I'll have turned 780,000 to 7,000. I can't do that. So what do I need to do to make sure that this 6 stays in the hundreds place?
We drop it down.
Well, no, what I need to do is I need to add zeros to hold place value. So if that 6 is supposed to be 600, I add 2 zeros so that it's 600. Because this was 780,582, right? So when I
Mm-hmm.
rounded it up, I have to round it to the nearest hundred to round it to the nearest hundred to the place value of that 5. So I mean, I add zeros to keep the place value the same.
Okay.
All right, what about the last one? This is a little tricky.
Mm-hmm.
What should I? What should this round to?
2000.
2,000. Very good. Yeah, because if I go 1, 2, 3, 4, this last significant figure rounds up. This is going to round this up, which causes this to get rounded up, which causes this to get rounded up, which causes this to get rounded up.
Mm.
And you end up with 2,000. Now, is it just like this? Is it just 2,000? Is that how I would write it?
2000. Think so.
And close. There's one thing that we have to consider though. The last significant figure, the last significant figure here, that 9, that's in the ones place. So I need to have significant figures all the way to the ones place. That means the last significant figure is in the ones place. That means this needs to be significant. The way it's written now, 2,000, there's no decimal, right? So is
Mm-hmm.
that,
Yes.
so is that last zero significant right now?
No.
So what do I need to do to make it significant?
You have to, yeah, put a decimal.
Yeah, I have to add a decimal. So I add a decimal to make it significant. Now I have the correct number of significant figures. Cool. Very well done. All right, let's do a little practice. I'm going to give you all a minute to go ahead and go through these and round these to the appropriate number of significant figures. In this case, you're going to want to try to round them to 3 significant figures. So last time we did 4. This time we're going to do 3. I'll do the first one together with you. So once again, remember you go left to right, underline the first 3 sig figs. 1, 2, 3. And then you round it up or down based on the number that comes after it. That would be this number. So this rounds to what? This would be 1.5 what?
59.
Well, not 59. This rounds the 5 up. So it'd be 1.56.
Oh,
Does that make sense?
yes.
Anybody? Okay, cool. All right, go ahead and try the others. I'll give you a couple minutes to do the other two, and then we'll go over them together. Okay, let's take a look at it. So what did, and you can feel free to type it in the chat if you'd rather, or you can just say the number out loud. So what do we have for the first one? Or what do we have for the, okay, the 0.003741? What did y'all get? Excellent. Oh, ooh, almost, almost. So the
I, I,
0.0374, what did you get?
I got 0.038.
Okay, so they're not quite right. Now, the thing here is you have to keep in mind those two zeros in the front, even though they're not significant, they're still necessary. We need to leave them there. So
Oh,
it does need, but they're not significant. So this is going to underline our first three sig figs. It's right, this 3.00374. So the answer is going to be 0.00374, the two rounds down. What about the next one? 1367. How would we round that one? Perfect. 1370, exactly. Excellent. There's the 136. The 6 is the last significant figure. It rounds up because of the 7, but you need to add a 0 for place value. Awesome. What about the next one? 128,522. Round that to three significant figures. What do you have? Excellent. 129,000. That's exactly right. And what about the last one then? The number in scientific notation. Very good. Yep. 1.67 times 10 to the negative 6. Excellent, excellent, excellent. Very good. So let's take a look at adding and subtracting. So when you're adding and subtracting with significant figures, it you have to keep track. You have to account for the uncertainty. So of course, the last significant figure tells you where the uncertainty is. So this is uncertain to the hundredths place. So therefore, it's plus or minus 0.01. The 5 is the last significant figure here, and it's the tenths place. So this is plus or minus 0.1, or plus or minus simply 0.1 if I want to just get rid of that 0 because it's not really necessary. So what's larger, a tenth or a 100th? Which one is larger?
100.
100 is larger, but 1/100th or 0.01, that's smaller, right? That's smaller than
Yes.
0.1. So the tenth is a larger uncertainty, and therefore when I'm adding or subtracting measured values, my final answer has to have the same uncertainty as whichever one has the largest uncertainty. In other words, it has to have the same precision, same uncertainty as the least precise measurement. And the least precise measurement in this case is the 1 to the 10th place. So another way you can look at this, so since the uncertainty is in the 10th place and that's a larger uncertainty, I have to round my answer to the 10th place. Another way you can do this, it's also actually maybe a little bit easier to see, is if you line them up along the decimal. What you can do is you can go left to right until one of the numbers stops having significant figures. In this case, the bottom number stops having significant figures after the 10th place. So you just draw that line down, and there you go. And so what that means is that now you round your answer to the 10th place, because that's where, now of course, if you actually added this up in the calculator, it would be 129.06. But because the last significant figure is the 10th place, this rounds up because of the 6, and it ends up being 129.1. The key idea here is that when you add or subtract numbers, you have to add or subtract their uncertainty as well, or error. Um, so when you're adding and subtracting, it doesn't matter how many significant figures you have, it only matters where the uncertainty is. Notice that this first number actually has 5 significant figures, the 124.56, but the second number only has 2 significant figures, and yet the answer has 4 significant figures. So the number of significant figures are all over the place. Sometimes you might have a number that has 3 sig figs, another one with 3 sig figs, you add them, and you get a number that has 4 significant figures. So you can gain or lose significant figures when you're adding and subtracting, because it doesn't matter how many sig figs, only where they are. Another way of looking at it that might be a little bit easier for you, I'm not sure if your professor described it this way, but you can also just look at the number of places past the decimal. Of course, this only works if each of the numbers has a decimal. If it doesn't have a decimal, you'll have to use one of the other methods that I described. So the answer has to have the same number of places past the decimal as whatever value has the fewest decimal places. So in this case, this first number here has 2 digits past the decimal place. The one on the bottom has 5 digits after the decimal point. So therefore, which has the fewest? The 2. And therefore the answer has 2 digits past the decimal point. Does that make sense?
Yes.
Cool. Now, whatever way works easiest for you, or makes most sense to you, or works easiest for you, go ahead and use that method.
Okay.
But those are 3 ways of looking at it. Now let's do a little bit of practice. So we'll go ahead and do the first one together. So in this case, I'm looking at the 0.56. What's the last uncertain digit? What's the last significant figure in the 0.56?
6.
The 6. And that's in the 100th place, right?
Yes.
The last significant figure in the 0.153 is what?
The 3.
The 3. And that's in the 1000th place. So which has a greater uncertainty? The 0.56 or the 100th place, the 0.56, or the 1000th place, the 0.153? Which has the greater uncertainty?
The 0.56.
The 0.56, the 100th place. So I'm going to stop my answer in the 100th place. I'm going to stop my answer at 2 decimals. So the calculator gives me the answer 0.713, but I'm going to record the answer as 0.71. Does that make sense?
Okay.
So let's go ahead and try the next 3. I'll give you a couple minutes to do this, and then we'll go over them. All right, let's take a look. Okay. So what did you get? What did you get for the first one? What do you get for the? Well, it's not the first one. The second one. This one.
Yeah, the second, I'm still kind of a little bit confused on that.
Okay.
A lot of numbers.
Yeah, no problem. Let's take a look at it. Let's take a look at it. Okay. So if I were to look at the first number, 82, the 82,000, what's the last significant figure there?
The 2.
The 2. So this is the nearest thousands place. What's the last significant figure in the next number?
The 2 as well.
The 2 as well. Only this one's in the hundredths place, right? So which is
Yes.
larger? An uncertainty in the hundredths place or an uncertainty in the thousands place?
The 100th place.
Oh no, 1,000,
No?
1,000, 1,000. This 82,000, see, if that last significant figure is in the thousands place, that means this is plus or minus
Oh, yeah.
1,000. Yeah, that's a huge uncertainty, much bigger than
Yeah.
1/100. So if I compare these two uncertainties, the first one has the larger uncertainty, so my answer has to stop in the place value of that uncertainty. It has to stop here. Alternatively, if you were to write this out and line them up along where the decimal point would be, here's their
Mhm.
82,000, and here's your 5.32. If I am adding these up, I go left to right until one of the numbers stops having significant figures. Well, that's right here. So 82,000, yeah, of course, the calculator spits out 82,005.32. However, my significant figures stopped way back here. I have to round that 2 up or down based on what comes after it. What comes after it is this 0. So the answer here is just going to be 82,000.
Okay.
Does that make sense?
Yes, because you cannot round it up because it's a 0.
Exactly. Exactly. All right, so now let's take a look at the next one. What did you get for the next one, or did you not get a chance to try that one?
No, I didn't get a chance to try that one.
Okay, well let's try to work it out together. What's the last significant figure in the first number? In this number, 10.0. What's the last? Where's the last significant figure?
The 0?
The 0. Very good. Tens place. Where's the last significant figure in the second number?
The 2?
The 2. So which one, looking at this, which one has a larger uncertainty?
9.8742.
Oh no. This one has 9.8742. That that 2 is in the 10,000s place. That's plus or minus 0.001, whereas the 10.0 is plus or minus zero point 0.1. Zero point 0.1 is much bigger than 0.0001, right?
Mhm. You're right.
So, and also you could go by decimal places since they both have decimal points. This has 4 decimal places, this has 1. I have to go with the fewer decimal points, or 1. Or if I
Okay.
look at uncertainty, I have to round this to the greater uncertainty, which is the tenths place. So if I round this number here to the tenths place, what do I get?
12, 60. 1260.
Not exactly. It's just going to be zero point 0.1
Okay.
because this is I have to round it to the place value of the larger uncertainty. This uncertainty is in the tenths place. This is in the 10,000ths place. The tenths place is the larger uncertainty, so I have to stop it in the tenths place, which is right here. That's
Okay.
the tenths place. I rounds up or down based on the 2 that comes after it. So the 2 is going to round it
Mhm.
down. It's just going to be zero point 0.1.
Okay.
Or if I go by decimal places, this has 1 decimal place, this has 4. I have to take my answer to only 1 decimal place, which means that
Mhm.
zero point 0.1, and it rounds down because of the 2 after.
Okay.
Does that help?
Yes.
Any
I'm
questions
still a
on
little
that?
confused, but I'm gonna practice more on it.
Okay. Yeah, I mean, likewise, if it helps to write it out, line it up along the
Mm.
decimal, you can kind of
Okay.
go, you can do that too. So you got 9.8. Ooh, that's kind of ugly. What did I do there? Let's do that. Let's try it again. 10. All right. 9.8742. So if I line it up along the decimal point, I go left to right until one of the numbers stops having significant figures. Significant figures stop here. So my answer stops there. This ends up being 0.1258. Yeah. But this is my last significant figure, so it rounds down to 0.1.
Mhm. Okay.
All right, go ahead and take a second with the last one and tell me what you get. What do you think? You got it?
No.
How about our other illustrious student? You've been getting them all right all night. You've been doing awesome. What did you get? What do you get for our last one?
I'm actually not sure.
Okay, this is actually kind of a trick question, if I had to be honest with you. Basically, the last significant figure in this one is the one. It only has one significant figure. There's no decimal point. See, there's no decimal point there. So that only has one significant figure, and that's in the tens place. Um, However, the last significant figure here is in the 10,000s place. So I have to stop my answer in the tens place. Well, if I look at the tens place, well, you know, the tens place is way out here, right? Now, when I'm talking about the tens place and hundreds place and such, y'all know what I mean, or am I kind of like confusing you? Because it's something that's not really taught very much anymore in elementary school. Probably hasn't been for quite a few many years, and I'm showing my age here. But um, do you know what I mean when I talk about place value?
Yes.
Okay, good. So,
Yes.
but yeah, so this is the tens place here, that where I've underlined it's 10, because each value, if I increase it up or down, if it make it go up or whatever, it's going to change it by 10. And then the ones place is right next to it, etc. So since the uncertainty in the first number is in the tens place, the uncertainty in the last number is in the hundred thousands place, or 10,000s place, the 10 is obviously a larger uncertainty, and I have to stop my answer there. But if you look at, well, that's a zero, and the number after it is also a zero. So if you round zero down, you get zero. This is a case where the answer would literally just be zero. Does that make sense?
Yeah, I was thinking that, but I was like, nah.
Yeah, no, I understand. Yeah, it's kind of like, what? No, it can't be that. It can't be that. But yeah, so the adding and subtracting is the hardest rule. It's the hardest rule to use. And it's more understandable why we use it, because you can understand, like, for example, if I have 10.56 and now I am adding, you know, 7.2 to it, if this is uncertain, if I don't even know the tenths place, how can I know the hundredths place, right? So the fact that the uncertainty is there's uncertainty in the tenths place means I have to stop right there because I can't have two uncertain digits. So this makes sense. It's actually pretty easy to understand why we have the rule that we do, but using the rule is a little tricky. Using the rule is a little bit not obvious, shall we say. But the multiplication and dividing rule is actually really easy to use. It's just a little bit more complicated to understand. So the product or quotient of two or more measured values must have the same number of significant figures as the measured value with the fewest sig figs. So like if I multiply a number that has four significant figures like this one by a number that has two significant figures like this one, my answer is going to have the lesser number of sig figs, 2. Does that make sense?
Yes.
So for adding and subtracting, it's where the last significant figure is. But for multiplying and dividing, it's where the it's how many sig figs you have. So don't get those two confused. It is kind of important. Let's take a look at some practice. Now, obviously, you are not likely to do these calculations in your head, right? 32.27 times 1.54. What is it? I was kidding. You're not going to do that in your head. You're going to do it in your calculator probably because you don't want to. I mean, even if you had a test and even if you're awesome at math and you know exactly how to do it and you can do it even relatively quickly, if you have a test, you're not going to have time for that, right? You're just going to put it in your calculator and calculate it. Well, your calculator is going to spit out an answer. And the answer it spits out is not going to be the one with correct number of sig figs. You're going to have to round it to the correct number of sig figs. So let's look at this. So the first number here, I have a 32.27. How many sig figs is that?
4.
4. And then there's 1.54. How many sig figs is that?
3.
3. So how many significant figures should my answer have? Remember the rule?
Less than 7.
Well, no, it should have whichever one is less. Which one has less significant figures? The 4 or the 3?
1.54.
Yeah, that only has 3 sig figs, right? So that means my
Yes.
answer is only going to have 3. It's going to have the same number of sig figs as my least precise measurement. Let me repeat that. The answer is going to have the same number of significant figures as your least precise measurement. And the least precise measurement, of course, is the one with the fewest significant figures, right?
Mm-hmm.
So if I want to round this to 3 significant figures, what do I get? You can type it in the chat or turn on your mic and tell me directly, whichever you prefer. Yep, 49.7. Very good. Now, let's do the next one. How many significant figures are in this one?
First one is 3. 3.68.
Yep, that's 3 sig figs. What about the second one?
The second one, 6.
Oh, you forgot your rules of 0.
Uh-oh.
Yeah, leading zeros are never
4.
significant, right? So how many significant figures does this have?
Yes, right. 4.
4, there you go. So which one has less significant figures? The 3 or the 4?
A 3.
Yeah, so how many sig figs should your answer have?
2.
No? Remember, it always has the same number as
No,
your
3.
3.
My
There you
bad.
go.
3.
No, it's totally fine. Good, there you go. Yeah, absolutely, it's 3. So that means you're going to round this one to 46.4. Okay, go ahead and take a
Point
moment
5.
to knock out the last ones. Now, keep in mind, it's already been calculated for you. All you have to do is write it down with the correct number of significant figures. Actually, you know what? I just noticed we are close to being out of time, so I want to go ahead and get through these before we're done. So I'll just kind of go through them real quickly. I hope you don't mind.
No, I don't mind.
So this one, the trailing zero is significant. That is 4. Leading zeros are not. Trailing zeros are. That has 6. So between 4 and 6, the 1.750 has less sig figs. I need 4 significant figures in my answer. In this case, it turns out that it already has 4 significant figures. So my answer is 0.05985. The next one, that's 5 significant figures. The 0 is significant because of the decimal point. And here I have 4 significant figures. 5 and 4, 4 is less. I have 4 significant figures in my answer here. If I count left to right, the last significant figure is this 6. It rounds down. So 1.586 times 10 to the 7. And the last one is kind of tricky. This is a very important number, which you'll learn more about later. But this is 4 significant figures. And this is also for significant figures. Keep in mind, of course, the times 10 to the 24th, that's just a place value holder. Times 10 to the 23rd is just a place value holder. It doesn't affect sig figs. So 4 sig figs and 4 sig figs. My answer should have 4 significant figures. But this only has 1. If you get a case where things kind of end up being, looks like they're whole numbers or something like that, and you don't have enough significant figures, remember you have to add the appropriate number of significant figures by putting decimal points and zeros as needed. So the answer here will be 1.000. Well, I hope that helped. That brings us to the end of our session. So now you know how to multiply and divide and with significant figures, add and subtract with significant figures, and you know how to identify the number of significant figures and where significant figures come from. So I hope that was helpful for you, and thank you so much for coming.